Good afternoon. My name is Angie DiNardo, and I'm Parker Hannafin's Pneumatics Territory Manager. This tool was created to help you size and select your pneumatic and electromechanical actuators. This webinar should last about 30 minutes. Feel free to reach out to us if you have any questions about this tool or if you would like future pneumatic assistance. The agenda today will be going over various challenges faced by engineers, an explanation of the tool, and also I will demonstrate the tool and go through a few examples. In today's busy economy, corporations are consistently trying to find ways to reduce their spend. Design engineers can reduce their spend through reducing the time associated with sizing a system, in addition, by working on numerous projects at the same time. Design engineers run into challenges when it comes to the complexity of sizing and selecting products. This is because they're working with a variety of different technologies, such as pneumatics and electromechanical. They have a variety of different application parameters, and they're dealing with multiple calculations to have to ensure that you're choosing the right product. In the end, design engineers want to feel confident in the product that they are specifying and selecting. And sometimes this leads to over-specifying or over-speccing a product, which can, in the end, lead to an underperforming machine. Parker is proud to present our online electric and pneumatic actuator sizing tool. Now it's easier than ever for design engineers to take an application concept to a completed solution. Virtual Engineer captures the parameters of your application data and quickly optimizes the results based on factors that are important to you. This tool provides an interactive 3D visuals to accurately model your application, and Virtual Engineer provides instant application assistance and the ability to size and select your actuator without having to pick up the phone or even send an email. The platform automatically runs thousands of calculations behind the scenes to ensure that you are choosing the most accurate product for your application. Not only does it give you the ability to size and select your actuator, but it also provides a collaborative development process by creating an online workspace for both engineers to share their project with their team members, as well as other Parker resources or your distributor that you're working with. The workspace allows quick access to saved projects, notes, and CAD models. In addition, the tool streamlines the process of quotation by automatically creating a bill of materials and securing the project in your online workspace. You are able to compare a variety of different products by various attributes that are relevant to you, such as air consumption, max force, breakaway pressure, and cost. The tool was predominantly designed for design engineers, and it is not a tool made to simply configure a part number. There's a lot more that goes into it. We have part number configurators for that. This tool is something you would use if you're trying to size a new system or if you would like to upgrade an existing system. The virtual engineering tool was created for both sizing electromechanical actuators and pneumatic actuators. Today we focused on sizing pneumatic actuators, but if you have additional questions on how to size electric actuators, feel free to reach out to myself or to our G group, and we can point you in the right direction to our electromechanical territory manager. We also are available for providing hands-on lunch and learns and demonstrations of the tool if you would like us to run through one of your applications and size it for you using the Virtual Engineer tool. There are 4 primary functions of the Virtual Engineering tool. You can size and select pneumatic and electric actuators and compare various product series. You're able to save your projects and share them with your other team members, as well as share them with Parker resources if you would ever like our engineers to check your work. You can easily request a quote and save and download CAD files. All right, let's jump into the tool so I can demonstrate how this works. To access Virtual Engineer, you can use the link on the screen, or you can go to Google and search Parker Hannafin Virtual Engineer. This is the main landing page of the Virtual Engineering tool, And if you ever would like to get a quick video, you can click this button here and it will lead you to about a 2-minute video summarizing the virtual engineering tool. To access the electromechanical actuator sizing tool, you can click this icon down here. To access the pneumatic actuator tool, choose pneumatics. After you choose the pneumatic icon, you have the choice to choose either linear motion or arc of motion. Arc of motion would be if there was a lever involved. For example, if you have an actuator extending and pushing a lever arm, that would be creating some motion. So you can size either just simple linear motion or also arc of motion using this virtual engineering tool. For today's examples, I will demonstrate the linear motion tool, but feel free to reach out to me if you ever have questions on arc of motion. This is the main page for Virtual Engineer. At the top, you can see that there's metric and imperial units. You can choose whether you want to work in metric or imperial. I personally like to work in imperial, so I'll switch that over. Below the units is a link that says, go to my projects, and up until this point, you had not had to log into Virtual Engineer. The only reason you would want to log in and create a free login is if you want to save and share your projects with your other team members. If you just want to explore the tool, you do not need to make a login. Below that is an icon that says Live Help, Ask an Engineer. This icon directly links to our application engineering support team. So if you're working through an example and you have any questions on an input, feel free to message them if you see this icon. Anytime that you can see this icon, it means that someone is online and available to help. Once you input all your application parameter information on the left-hand side, it will generate results, will change from gray to yellow, and also the compare feature. So once you enter your critical information, you will then be able to generate and filter your results. Below, you have your operating parameters, and it's important to note that anything in a red box means that it's critical information and you must input a parameter. And if you ever have questions on what a parameter means, for example, it says enter the tubing length, you can hover over the question mark and it will explain it. So it says tubing length is the distance from the valve to the actuator. So it gives you a better explanation of what that parameter is looking for. Also, if you click on the overview, and at the bottom it says click here to view the detailed guide. What this detailed guide is it goes through an explanation of each of these parameters and everything below to help you be able to choose and fill in the right information for your application. It just gives you a better detailed explanation of each of the parameters that the tool is asking you for. Below is the application type, and you can choose 3 different applications. Either a spanned application, which would be something similar to a rodless cylinder, cantilevered, or a stopper cylinder. So this would be if you have a cylinder on a conveyor line and the cylinder is extending to stop a package or stop a box, that would be considered a stopper application. For some of the applications types, you're able to choose between 2 pictures. It's important to note that it's okay whichever picture you choose, it won't impact your results, but you can choose whichever one looks most like the application that you're trying to size. Below is the orientation of the actuator. In this screen, you want to orientate your actuator exactly how it would be mounted on your machine, because all those calculations will go into the software and it will make sure that you're choosing the right product for your application. For example, if you have it mounted vertically with the cap end facing down, you want to make sure that you orientate that correctly, because center of gravity needs to be taken into consideration. In this area, you can also account for the attached mass. For example, if you have a tooling plate and it's threaded to the end of your cylinder, you will want to enter the weight of that attached mass, for example, 10 pounds. And then also the X, Y, and Z axes account for whatever the center of gravity is for that attached mass. And that is illustrated as the yellow box. So this yellow box represents the center of gravity for the attached mass. And as you change the various axes, it will change the orientation of the yellow box. For example, if we have a 5-inch offset in the Y direction, you can see that it did change. And then maybe we have a 3-inch offset in the Z direction. You can also see how that has changed. So just to recap, it's important to orient your actuator in the correct orientation that it will be mounted onto your machine. Below is the motion details, and the first area is entering the required life. It automatically defaults to 1,000,000 cycles, and then it will show you at the end what our actuator's life cycles ratings are. If you have a customer or an application that you need at least, for example, 10,000,000 cycles, feel free to write that down right here. But if not, you can just leave it at 1,000,000, and at the end, you'll be able to compare all the actuators based on whatever their life cycles are. Below is the stroke length. So if say you have a stroke of maybe 10 inches, and then you have extend and retract information. So is it a double acting cylinder or is it a single acting cylinder? If it's a single acting, is it a spring return or a spring extend? So all that information is important to know to make sure that you're going to get the correct product at the end. So then it asks for what is the extend time. So in 10 inches of stroke, how fast is that actuator going to be extended? So for this, you could say, all right, it's going to extend in a half a second, 10 inches. And then dwell refers to once it's extended, is it going to be holding that extension position for an extended period of time, or is it going to be retracting instantaneously? So maybe we could say it's going to extend in a half a second, it's going to stay for 1 second, and then it's going to retract again in 1 second, and then dwell for another second. And this is important to note if you are concerned about the life cycles. As you can see, once we inputted this information on the left, the cycle time did change on the right. And then you can even get as much specific information as you have by adding the hours during the day that this application would be in use and how many weeks per year, so that you get a real accurate reading of the life cycle. Here's the external forces area, and it's important that you do include as much information that you know about your application as possible to ensure that we are choosing the right product for you. The first question is there an external stop? Yes or no. So this would be if you have a cylinder where, say, the stroke is 10 inches, but there is something obstructing the stroke so that it's a physical barrier not allowing the cylinder to fully stroke out. Maybe there's something in the way at 8 inches. So you would want to make sure that you include that information and say, yes, there is an external stop, and input that information there. The next question is the customer going to provide a load support? Yes or no? And this would be if you know that you have an application where there is side loading and you are going to provide the guided system and bearings, you would say yes, you are providing the load support, and then you would enter whatever the coefficient of friction is for those bearings. And then at the bottom here, it says the coefficient of friction of the pushed mass. So if you have an actuator that's pushing a box on a conveyor line, you would want to know what the coefficient of friction is between that box and that conveyor. So maybe it's steel on steel, aluminum on steel. So we'll say no. And then below you have forces, moments, and additional forces. So in the force section, this would be any external forces that the application is going to encounter. You would choose if it's the force is only in the extend, the retract, or in both directions. And if it's during the entire length of the stroke, for example, is it 0 to 10 inches, or is it just hitting in the middle of the stroke, so maybe 5 inches to 10? And then you would put whatever the force is. So maybe it's 10 pounds per force. Then you can see at the bottom, as we entered 10 pounds per force, the arrows indicating the force did show up. If you changed it and said the force is actually acting in a different direction, you could add a negative, and you can see that the arrows are actually for the force pushing in towards the cap end of the cylinder. And then the next section is moments, and you can choose whether a moment is encountered in the extend, retract, or both as well, and where in the stroke is it going to be encountered. So you can say it's acting throughout maybe the last inch of the stroke. And an external moment would be something, for example, if you have an actuator and there's a drill bit attached to the end of the actuator, and that drill bit is actually providing some torque and causing rotation at the end of that rod. So that would want to be accounted for. You would not need to enter any information on if you have a non-symmetric tooling plate that would be causing a moment. If you entered that information above, the tool will actually calculate whatever moments are associated with that. So we can put a moment here. We'll say again 20 pounds per force. And then you would want to change the display below from force to moments. And you can see that the arrows for indicating the moment did come up. And then if you wanted to change the direction of that moment, you could add a negative. And then we could say also maybe there's a positive 40. And it's nice because you can actually move the actuator and visually see how the moments are showing up in your application. And then below you have additional forces. So if you have an actuator that's running into a spring, you want to take into account that external force. If you have a box, again, for example, extending on a conveyor line, pushing an attached mass, or pushing a mass, you would want to do pushing mass. And then you would want to say if it's in both directions or if it's only in the extend or the retract direction. And you can say where in the stroke is that attached mass going to encounter, or where in the stroke is that pushed mass going to encounter this actuator. So maybe it's at the beginning to the end. And then if there's any offsets of that pushed mass and what that weight is of that pushed mass. And then again, if you have an attached mass, so this is not the tolling plate because that was already taken into account in the above section. So now let's walk through an example of an actual application and size it using the virtual engineering tool. So you have an application where two cylinders are extending and retracting and pushing boxes into another box. It's a standard temperature and pressure. The valve is mounted 10 inches away from the actuator. It's a symmetric tooling plate weighing 3 pounds at the end of the rod. You require 5 million cycles of life. The stroke is 12 inches. The extend time is 1 second. It dwells for a second, retracts in a half a second, and then dwells for 2 seconds. It is a double acting cylinder, and the coefficient of friction is 0.15. And those 6 boxes weigh in total 30 pounds. It does need to be compatible with sensors, and the question is, what is the most cost-effective option, and what is the CV value needed for a valve for this cylinder? So now let's go back into the virtual engineering tool, and we'll reset our application parameters. So I will toggle this back over to Imperial. And the application stated standard operating and temperature, or operating pressure and temperature. The tubing length was 10 inches away from the actuator. It's a cantilevered type of application. The orientation of the actuator is not horizontal, is not vertically, it is horizontal, so this is actually fine. And it is a symmetric tolling plate, so we don't need to enter any axis information since it's not off center. The attached mass of the tolling plate is 3 pounds. The customer is not providing a load support, so if there is a guided system that is needed, I would like Parker to recommend that system to me. We need 5 million cycles. The stroke length is 12 inches. It is a double acting cylinder extending in 1 second, dwelling for 1 second. So let's jump back into the virtual engineering tool and enter the application information. We'll reset the parameters first. And then at the top, I will toggle back over to Imperial. It is standard operating pressure and temperature with a tubing length of 10 inches. It's a cantilevered application, and the actuator is oriented horizontally, not vertically. It's a symmetric tolling plate that weighs 3 pounds, and there is no offset, so because it is symmetric. The customer is not providing a load support, so I would like Parker to recommend a guided system if it is needed. The required life is 5 million cycles with a stroke length of 12 inches. It's a double acting cylinder and it extends in 1 second, dwells for 1 second, retracts in a half a second, and dwells for 2 seconds. There's no external stop, and again, the customer is not providing a load support. It is a pushing mass, and the coefficient of friction is 0.15. I know that there is the mass or the force of the pushed boxes. So there's a pushing force and the extend only, and it's throughout the entire stroke. So it's from 0 to 12 inches. And the mass of the 6 boxes total was 30 pounds. And there is no Y or Z offset since it is hitting the center of the rod. So now that we've inputted this information, we can go up and generate results. So as you can see now, generate results is highlighted in yellow. And it usually takes a few seconds to load the results since there are thousands and millions of calculations actually going on behind the scenes to ensure that you are getting the right product. So now you can see a variety of different product series that Parker would recommend. A 4MA cylinder, a P1D, an SR, and then the guided systems are not till the end because there really isn't much side loading, if any. And so you really don't need to use a guided system in this type of application. So it'd be more cost effective and it would be more correct for your application to actually use a non-guided system. So what you can do is actually compare these various product series, check them all and say compare. And the question was, what is the most effective cost option and what is the CV value needed for the actuator? So before we choose the actual actuator, I want to point out that you can actually choose a few different columns to compare in attributes. For example, right now you can see the relative price, lead time, and life. Relative price is, if, for example, this SR cylinder that is 1.75 inches in diameter is the least expensive option, and everything up from it. So an SR cylinder with a 2-inch bore is 9% more expensive than a SR cylinder with a 1.75-inch bore. So here are the various application attributes that you can actually compare. So maybe you want to compare various mounting, the theoretical forces, the breakaway force. I know the question said, what is the CV value? Maybe you're concerned about air consumption and you want to choose an actuator that has a low air consumption, or breakaway force is important. Or maybe you have a small envelope, so you want something with a small diameter. So you can choose whatever attributes are important to you. And then the option is, what is the CV value and what is the most cost-effective option? So it looks like this SR series cylinder will have 11.2 million cycles of life. It requires a 0.38 CV value valve. So you can go ahead and now size your valve. And then what we want to do is configure it and get the final part number so that we can save it in our projects. So as you can see, it already has the pre-selected options included. Piston type, if you want bumpers. Rod end style, you could do special or standard. And these are all options that would not require much engineering. It's really specific to your application. For example, port type, threads, if you want maybe a magnetic piston. Stroke. So you can see on the right-hand side, it says pre-selected value of 12 inches, since that was what was inputted in the tool. And then you can either generate a CAD here, you can save it. So we'll go ahead and save. Or, you know, I think I chose generate CAD. Okay, so now I did choose save, and it is requiring me to use a login now. So we'll go ahead and log in. And on the right-hand side, you can see there is an area for creating an account. So now we can choose whatever folder we would like to save it to. So I will do here, project name, virtual engineer demo, a description, webinar, and it is a single actuator, and whatever the system name is. So maybe you have a project where you're working on a variety of different modules within it. So you could say this is the box pushing application. And you save it, and it will be in your project space. There we go. We have our one component for the box pushing application. We have the final part number, so you could go ahead and request a quote, get your CAD models. We could add notes to it. It does give you a summary. We don't have any notes or anything right now, but if you wanted to, you could share this. You could actually download the system if you wanted to keep a summary of it, or you could share your system, request a quote, or share your system with your other teammates. So now I'm actually going to go in and modify this example just to show you that if you get another application or the customer says, oh, the application changed a little bit, instead of having to go back in and redo everything, you can just come in and modify it. So you would go up to the corner and say edit sizing. And now for this example, all I'm going to change is make the stroke length longer and make the tooling plate heavier. And I want to just show you that this system will know that you now need a guided system. So everything else will remain the same, except the attached mass will go from 3 pounds to 10 pounds. And the stroke will go from 12 inches to 20 inches. Everything else remains the same, as well as down here will be the entire length, so 0 to 20. And then we can go up here and click generate results. And so it is a cantilevered load, so that 10 inches over a 20 inch stroke, or 10 pounds over a 20 inch stroke is going to produce side loading in a moment. So you would want to make sure that you do use a guided system for that. So we can say save progress for this. And it's now saved in your application, your projects. The reason you don't see a part number here is because we didn't go through and finish the configuration of it. So I'll go back to the PowerPoint. So thank you so much for your time today. As a summary, the virtual engineering tool provides an easy to use, interactive, collaborative workspace which allows you to size and select your pneumatic and electromechanical actuators, leading to time savings and accurate selection of products. Feel free to reach out to myself if you have any additional questions or if you would like hands-on pneumatic assistance. Thank you very much.